what is this k and what is this h? So k runs from 1 less than equal to k less than equal to m. Whenever you take x, it is either here. If it is not here, it has to be here. Obviously, it cannot be in both of them because they are disjoint. If it is here, then it cannot be the next one. So it is in exactly one of them. Because you are sure that it is exactly in one of them, you can actually define like this, and this is how we define. And by the very choice of this definition, you can, so this is defined. So define your step function from I to R by this. And remember, I'm not, because of the space constraint, I'm not writing. This x uniquely comes from one of these subintervals, and therefore it is quite right to define your function like this. And once you are able to define like this, by the very choice of your delta, it will automatically give you that this is happening by the choice of delta as per star. We easily get, what do you easily get? You easily get what you desire. Fx minus s epsilon x is less than epsilon for whatever point you take in your interval I. So without much difficulty, you are able to do this. But you can see what is the most important thing in this proof. Let us not try to run away, because if you understand the basics, then you can actually prove it in different cases also. The most fundamental thing what we have used here is the uniform continuity of a continuous function coming out of a closed and bounded interval. We know this, you have proved this in your classes, you can look into any standard book, you know that. Once you have that, you have taken that delta, and out of this choice of delta, you have found out a large m such that this is going to be smaller than why it should happen? Because of this. Because it goes to 0, so obviously it has to cross every possible positive number, and the moment you do that, delta is a positive number. For some m, it will cross it, you call that h. So obviously one can make larger and larger choice. My h could be different than your h and so on and so forth. That is always possible. But you choose such an h, and then you can go ahead with this kind of a discussion. So this is what you can see. So in that graph, you can see that we are now able to approximate a continuous function by a very simple kind of step functions. Step functions is the most simple function one can imagine. But now somebody will put a question to us that the function which is approximating is not continuous. This is a discontinuous function. Of course, you leave the trivial cases when you are taking a step function which is taking a constant value on the entire interval. That kind of function you leave. But in most of the non-trivial cases, the step functions are discontinuous. You can obviously see that, right? Why they are discontinuous? I can again go back to my graph. Graph is one very simple method to understand analysis very well. One must resort to that. You can see this is a typical step function. So there are steps, you can see there are lines, small segments, and of course when you are traveling on that segment, when you go to the next segment, you are making a jump either upward or downward. So this is a discontinuous function. So the lacuna or so-called lacuna or the deficiency, one can say, okay, we have obtained this, but this is not continuous. How to approximate it? By a simple kind of a continuous functions which are more simpler, because as I said, your continuous functions can be very complicated. For example, just for the sake of information, I think many of you might not have read. What is possible, I can tell you something, that there exists a continuous function. There exists a continuous function from this line. This line means this is an interval. And what is this? This is just a box. This is just a square or a rectangle. And you can actually replace it by any n-gon or anything. Now the result is there exists a continuous function g such that something beautiful happens. So suppose this is I and this is inside field, right? This is inside field. I am taking this is inside field, right? So suppose this I am calling it, say, S. So one can always find a continuous function from a line into a square such that the image is whole of a square. Something very, very unnatural, which was very, very difficult to be believed when it was initially done. Yeah, you can always, so okay, what one can do is, you have this line, you can break this line into 2 pieces and you can have this. You can break this line into 3 pieces and you can have this. You can break this line into 4 pieces and you can have this. You can have a pentagon. You can have a hexagon. You can have any n-gon. So a line can be, why? How you can do this? You break it into 5 pieces and map this to this, map this one to this one, and so on. So you can actually do this. This is possible. But this is amazing that you can have a continuous function filling the entire space in this square. Obviously, such a function cannot be differentiable in this case. Of course, the proof is beyond the scope of this lecture. So what I am trying to indicate you is that continuous functions can be very complicated in nature. You can imagine how this function can be constructed. So some standard little bit, some books I can refer. For example, one can refer the books of Moncrief or Simmons. There are some standard authors writing books on metric spaces or topological spaces. Don't worry if you are not knowing topological spaces. Metric space you can just concentrate. So there you can see that such proofs. So this is called space filling curves. A popular name is space filling curve. What is a curve, by the way? Curve is a continuous image of a line or a line segment, right? Or an interval. So space filling curve. So continuous functions can be very complicated, but what is that we have achieved is that any complicated continuous function you take, you can always find a step function through which you can approximate. Now let us address the discontinuity part. The question somebody can raise and might have raised, I cannot hear any one of you, that this function is, approximating function is a step function which is discontinuous. Can we have something which is continuous as well as approximating this? Yes, we can. We will slightly improvise this situation. So what is the next thing what I am going to write here? This also could have been written as a theorem, but okay. What I am saying is this. So I am assuming the same thing. You have, I am not writing all the words because let us save some time. Let us do a little more work, whatever is possible. This is any function which is continuous, and epsilon is some constant which is greater than 0. We have an epsilon which is greater than 0. These are given things, right? These are given. Then what we can find? Then there exists a piecewise linear continuous function, right? What is linear? Linear is line, right? So piecewise linear continuous function, say G, which of course will depend on epsilon, such that fx is as close as you wish. This is less than epsilon for all possible x belongs to I. This is the next step. So the previous case, what if you remember the graph, step function, but that is also one can say linear because there are only line segments. The line segment, these are just, so these are also linear. But there that was not discontinuous, right? Something like this. This was the function. Now piecewise linear, how do we do piecewise linear? Alright? How do we do piecewise linear? This is your interval A, this is your B, these are subintervals, for example. So I can have this up to this place. Then from here to here, if I have to go, then maybe I have to go here. From here to here, then maybe like this. Then from here, further like this. Then from here, further like this. So this is a typical example of piecewise linear function. This is just a piecewise linear. So everything is linear, piecewise, and this is continuous. Why? What has made it continuous? The end. If you look at the graph, the end point here and the beginning point here of the graphs, they are meeting. So that if you can ensure that, you will get a piecewise linear graph, linear function. So what? So now this is continuous, but yeah, from your basic knowledge of differentiability, you can say that this is not differentiable. Why is this not differentiable? Why is this not differentiable? Because there are sharp edges. Okay, what is the simplest function you know which is continuous but not differentiable? The first perhaps example you might have seen is modulus x. What is a modulus x? What is the graph of a modulus x? This is how you draw, right? This is the graph of a modulus x. And where do you say it is not differentiable? Which point? You say this is not differentiable. Why? Well, there is a sharp edge. Why? Because you can have so many tangents passing through this. Right? Right? So what is that we are saying? So this is failing to be differentiable at this place. Except this, otherwise mod x is, we know this is differentiable. So this function will be differentiable everywhere except at these endpoints. This point, this point, this point. No, this is not differentiable. We are not achieving differentiability. So obviously next question would be, okay, once we do this, you will then ask, okay, can we remove even this? We'll see that yes, we can remove this, and we can remove this very efficiently in the sense that at all places the approximating function will turn out to be infinitely many times differentiable. Yes, there will be C infinity function. Okay, what is C infinity function? A function which is differentiable as many times as you wish. For example, sine function. Differentiate. Can you differentiate? Yes. Cos. Can you differentiate cos? Yes. Can you differentiate sine? You keep on. So these are infinitely many times differentiable functions. Right? So you can do it by such functions. So okay, but before I come to that, for that I'll have to go to slide because some calculations we will make. But let me explain you how this you can do it. So you have to slightly modify these arguments and you can do it. So let us see how you can do that. How you can achieve. So let me indicate the proof of this part. Okay. Some of the constructions will go as we did last time. So for this epsilon, if you remember, so proof, right? I'm just giving you the hints. So right at the end, maybe I'll indicate you my email ID. You can, if you have any problems, you can get back to me as and when you want. You can speak to me. Okay. So what do? We use uniform continuity again. This is very powerful, right? People talk of applications. Come on, have a beautiful look at application of uniform continuity. Use uniform continuity of f. Right? So what do you obtain out of this if you use this? We obtain, yes, we obtain delta, which will of course depend on epsilon. If you are comfortable, you can drop this. But if you are not comfortable, just for the sake of clarity, emphasis, I am making this, that this delta depends on the choice of epsilon. It will not be depending on the choice of the points you make. We obtain delta, then obtain what? Do you remember what did we obtain last time in the previous proof? Yes. Then obtain what? H. How was H obtained? Yes. Yes. The H was obtained by just considering the sequence. B minus A is going to be difference of the endpoints of the closed interval I. N is a natural number. This is a sequence which goes to 0 as n tends to infinity. So it will cross every possible positive number. So you can always obtain large M, right? There exists M belongs to set of natural numbers such that B minus A by M is different from delta. This is your H, right? I hope you are able to recall this, that this is your H. So then obtain H. And once you obtain H, you subdivide your interval I into how many disjoint intervals? M disjoint intervals. What is the first interval? A, and travel up to A plus H. So A close, A plus H open. Then A plus H close, A plus 2H open. Then A plus 2H, A plus 3H. Continue this. At what stage we will reach B? Mth stage that we saw last time. So we'll have these sub pieces, right? So these intervals you have A plus H. I'm just going further, and this, the last one will be A plus M minus 1H, and this is B. Why I am closing it? Because we have not to proceed beyond B, so we are closing it at this stage. So these are the intervals. And on these intervals, how have you defined your function earlier? S epsilon of that, you can recall that. Now what is the care we take here? How do we define G? Define G as follows. Define G as follows. So it is sufficient to define G on each of these sub intervals. So how do we define G? So I am writing first interval, I am taking this on A plus H. I am taking this. G of X lies on what?